Hi class, today's video lesson is graphing exponential functions and looking at graphs and interpreting what it says. So this is 9.6 day 1. So on this first one, our directions here are to graph y equals 3 raised to the x. I want to point out one thing right away, and I want you guys to notice this as well. Your base right here is the number 3. Remember what we said from the very first day of this chapter was if it's a base that is greater than 1, okay, when the base is greater than 1, it's going to be exponential growth. And that means as x goes to the right, our graph is going to get bigger and bigger and bigger, like this. Okay, so that's what we can expect to see as we graph this one. So right away, your directions here, graph this. Let's just put it right into our graphing calculator. Y equals 3 raised to the x. So take out your graphing calculator. Y equals 3 raised to the x power. We graph it. And as you can see, we do see growth. We see as our graph goes to the right, our y values increase. So now what I want you to do here, class, is I want you to plot as many points on here as you are given with graph paper. Okay? It might sound like a lot, but it really isn't too bad. I want you to go to your table in your grapher. So second graph, which is the table. As you can see here, I'm not going to put these values on here, but I will start here. So at 0, 1, 1, 3, 2, 9, and 327. I want all 4 of those points on there. And hopefully this is pretty easy to see, because 3 raised to the 0 power is 1. 3 raised to the first power is 3. So when x is 1, y is 3. And then 3 squared is 9, so when x is 2, y is 9. And then when x is 3, 3 cubed is 27. So we get something that looks like that. Now I want you to see a couple points to the left of the y-axis as well, which means when x goes negative. So when x is a negative 1, notice how it is 0.333333333, or 1/3. And the same thing when x is a negative 2, it's 0.111111. I want you to put that on your graph as well. So going back here, when x is a negative 1, y is 1/3. As best you can, put that on there, and I'm not having too much luck with my little spot here, but something like that. Okay? And then this is right above the x-axis. So here's what my graph is going to look like. If I could connect these dots here. And like this, and then it goes up and to the right like this. As you can see here by looking at our table, if you keep on going negative, so negative 3, then negative 4, negative 5, negative 6, negative 7, so on and so forth, notice how it gets very, very small. I mean, at negative 10, it's 1.7 times 10 to the negative 5th. That's a very small number. However, it's still positive. So when it's still positive, I want you to see something on your graph. This red line right here is never going to go below the x-axis. Okay? It's always going to stay positive. So that's called an asymptote. Your asymptote is the x-axis, or the line y equals 0. So you can write that down in this asymptote part. Y equals 0. It's never going to go below the x-axis. So that's what I expect to see on your graph. Now just do the domain and the range, and this is pretty easy. Interval notation, that red line right here, it goes all the way infinitely to the left. So it goes from negative infinity, and how far to the right does it go? Well, class, I could continue putting in positive values for x all the way up until positive infinity. So this red line, it goes all the way to positive infinity. So from negative infinity all the way to positive infinity, which means that x, such that x belongs all the real numbers. Okay? So now for my y-axis, how low does this red line go? Well, remember how we said it goes infinitely to the left, but it doesn't go infinitely down. Okay? It doesn't ever hit 0. It's always going to stay positive. So it starts at 0. It doesn't equal it, so I'm going to have a parenthesis right there. And then how high does it go? This red line goes forever up. So it goes all the way to positive infinity. And we write that by saying y such that y is greater than 0. We don't write greater than or equal to because it's never going to equal 0. It's just going to be greater than. So that's how you do this problem. This is what I expect from you on a test. Let's do one more practice problem. On this one, hopefully you see your base as being 0.25. If your base is greater than 0, however, if it's less than 1, this is going to be exponential decay, which means as your graph goes to the right, it is going to decrease your y values. So every exponential decay is going to look something like this. Okay, so here's your growth, and your decay is this one. Okay, so that's how you could always check your work as you graph these in your graphing calculator as well. Let's put this into our graphing calculator, please. 0.25 raised to the x. Y equals 0.25 raised to the x power. And we graph this. And as you can see, we do have it decaying. It's going down and to the right. So let's plot some convenient points on our graph. Okay, it gets very, very large as you go to the left. As you go right, so -5, -4, -3 is 64, -2 is 16. That's probably going to be the first one we're going to put on our graph. And then at -1, it's at 4, 0, it's at 1, 1, it's at 1/4. So these 4 right here are the ones that we're going to put on our graph. Okay, -2, +16. -2, +16. -1, +4. At 0, it's at 1. And then at 1, it's at 0.25. So now from here, just like on the last one, it approached an asymptote. Look at what asymptote it approaches this time. This time, as x gets bigger and bigger and bigger, y gets smaller and smaller and smaller. So x is increasing 2 to 3 to 4 to 5, but my y's are getting smaller, 0.06, 0.01, 0.00, and then we have our scientific notation of these very, very, very small numbers. So once again, these aren't negative numbers though. They're very, very small, but they are positive. So that means our asymptote is once again going to be the x-axis, which is the line y equals 0. So our asymptote, y equals 0. It's never going to go negative. So let's connect these dots, and then it's going to follow our asymptote right here. Okay, that's what I expect to see on your guys' test. Now let's say what the domain and the range is. This green line goes infinitely to the left, and this green line goes infinitely to the right. So my domain, just like on my last one, is all the real numbers, from -infinity all the way to +infinity. My range, also very similar to the last one, it's never going to go negative. It's always going to stay above the x-axis. So that means it's going to start at 0, or actually just above it. It's never going to hit 0, so I'm going to have a parenthesis there. And then how high does this green line go? It goes infinitely up. So it goes all the way to +infinity. Which means that my range would be y such that y is greater than 0. Not greater than or equal to, just greater than. Okay, so hopefully those graphing problems aren't too difficult. Now we're going to interpret some information from these graphs. Here's what we have. This pesticide DDT was widely used in the United States until it was banned in 1972. This pesticide is toxic to a wide range of animals and aquatic life, and it is suspected to even cause cancer in humans, so we don't want this on our crops anymore. The half-life of DDT can be 15 or more years. Here's what half-life is. It is the amount of time it takes for half of the amount of the substance to decay. Scientists and environmentalists worry about such substances because these hazardous materials continue to be dangerous for many years after their disposal. So nature has its own way of taking care of certain substances, but it takes a little bit longer on some hazardous chemicals than we'd like to. So if we look at this one, the x-axis, each interval is 15 years. So when x is 1, it's actually 15 years. So 2 is 30, 3 is 45, 4 is 60, 5 is 75, 6 is 90, so on and so forth, okay? And then for our y-axis, each interval is grams of DDT remaining. So after 60 years, estimate how many grams of DDT remain. Well, what happened is it starts at 100 when it's at 0. So evidently they put 100 grams of DDT into this crop, whatever the case might be. Okay? And then estimate after 60 years, after 60 years, remember how this is 15, 30, 45, 60. So when x is 4, estimate where it is. It is right there. So what spot is that one when x is 4? It looks like it's maybe around 5 or 6. I would say it's just above that halfway point. So my y value, you see how this y value is 10. So right about here, as I would say, approximately 6 years. Okay? If we wanted to know exactly what it is, this does say approximate or estimate, so I would accept this on a test. However, class, if you want to see exactly what this is, they put 100 grams of DDT in the soil. Okay? So then, after 15 years, half of it is gone. So now this is 50. After 15 more years, half of it is gone. So this is 25. After 15 more years, half of it is gone. So this is 12.5. After 15 more years, half of it is gone. So now this is 6.25. So if we wanted to say exactly what it is, it would be exactly 6.25 grams. Or wait, what are we talking about? Yes, this should have been grams. 6.25 grams. Either one of these I would accept on a test. Okay, looking at this next one, one of the most common examples of exponential growth deals with bacteria. Bacteria can multiply at a very alarming rate when each bacteria splits into 2 new cells, thus doubling. For example, if we start off with 1 bacteria which can double every hour, by the end of the day, we will have over 16 million bacteria, and that is just ridiculous to me. So looking at number 4 here, it says after 14 hours, estimate the number of bacteria cells. So our x-axis is the number of hours. So here's 14 hours, okay? How many bacteria estimate, so once again approximately, the number of bacteria cells? Well, it's way up here. It's this value. What value is this one? Well, here's 16,000, here's 17,000. I would say maybe 16,500, if that's okay with everyone. Approximately 16,500. Okay? This is an answer that I would accept on a test or anything close to that. If we wanted to find out for sure or exactly how many bacteria cells we'd have, look at the pattern. After 1 hour, there's 2 bacteria cells. After 2 hours, it's 2 squared, which is 4 bacteria cells. After 3 hours, it's 2 cubed, which is 8. After 14 hours, it is 2 raised to the 14th. And what is 2 raised to the 14th? You could put that into your calculator, and it would be 16,384. So this would be exactly, this would be an approximate. So this is just interpreting these graphs, not too difficult. Our assignment is going to be a worksheet that is very similar to these notes. 2 problems on graphing, 2 problems on interpreting the graph. You also have your last of the Excel math objectives for this chapter. It's objectives 114 through 116. Be sure to let me know if you have any questions on that when you get to class tomorrow.